In this video, I will show you how to solve polynomial and rational inequalities. Let's start with the basics. We can solve this inequality by getting x by itself. Subtracting 6 from both sides, we have 2x is greater than negative 2. Dividing both sides by 2, we get x is greater than negative 1. You can either leave the solution as an inequality, or you can write the solution using interval notation. Here's another basic example. Subtracting 4 from both sides gives us negative 3x is less than or equal to 11. Next, we need to divide both sides by negative 3. But be careful. When you divide both sides by a negative number, you must reverse the direction of the inequality. So we end up with x is greater than or equal to negative 11 thirds. When you write the answer in interval notation, we use a bracket on the negative 11 thirds to show that this value is included in the solution because of the or equal to in greater than or equal to. By contrast, we used a parenthesis on the negative 1, not a bracket, because x must be greater than negative 1, but not equal to negative 1. So, to show that negative 1 is not included in the solution, we use a parenthesis. When a problem is a little bit more advanced, we need to get 0 on one side and factor. So let's begin by adding 3 to both sides. That leaves us with x squared minus 6x minus 27 is greater than 0. Now we factor. X squared will be x times x. 27 is 3 times 9. To get a negative 6 in the middle, we need a positive 3 and a negative 9. In a moment, I will solve this inequality by making a sign chart. I'm going to refer to the left side of this inequality as f of x. To make a sign chart, we need to know where f of x is equal to 0 or where f of x is undefined. Since a polynomial is defined everywhere, we don't have to worry about the second one on this particular problem. So let's just ask ourselves, where is f of x equal to 0? Using the zero product property, we can see that the left side of the inequality is equal to 0 at x equals negative 3. That's what we get if we set the first factor equal to 0. Or x equals positive 9. Negative 3 and 9 are called critical values. To make the sign chart, put your critical values on a number line across the top. Next, you will need a row for each factor of f of x. Finally, we need to decide whether these factors are positive or negative in each interval. Let's start with x plus 3. X plus 3 is equal to 0 right at negative 3. This factor will be negative to the left of negative 3 and positive to the right. For example, if x is anything bigger than negative 3, like let's say 0, then we have 0 plus 3, which is positive. If you pick any number to the left of negative 3, for example, negative 4 plus 3 would be negative 1. Similarly, x minus 9 is equal to 0 right at 9. This factor will be negative to the left of 9 and positive to the right. But what about the overall sign of f of x? Well, in this first interval, we have a negative times a negative. That's a positive. In the middle interval, it would be a positive times a negative, which is a negative. And in the third interval, we have a positive times a positive, which is a positive. Because f of x needs to be greater than 0, we are only interested in the intervals where f of x is positive. So the solutions will be here and here. Let's write the solution set using interval notation. This first interval goes from negative infinity to negative 3. And we use a parenthesis on the negative 3 to show that negative 3 itself is not a solution. Remember, we want values of x that will cause the function on the left to be greater than 0. At -3, f of x is equal to 0. So -3 should not be included, and we show that with a parenthesis. We have another interval right here, from 9 to infinity. Again, 9 is not included, so we use a parenthesis. So this is the solution for the first example. Let's try this one. I'm noticing that every term is divisible by 2. So let's start by dividing everything by 2. This leaves x squared minus 5x is less than or equal to x minus 8. Now let's get 0 on one side. We need to add x to both, no, we need to subtract x from both sides. And we need to add 8 to both sides. This will leave us with x squared minus 6x plus 8 is less than or equal to 0. Let's see if this will factor. X squared factors as x times x, and 8 can be factored as 2 times 4. To make a -6 in the middle, we need the -2 and the -4. Also, -2 times -4 is positive 8. So we factored it. The critical values are where f of x equals 0. This function on the left will equal 0 at x equals 2 or x equals 4. Let's put these on a number line to make a sign chart. Here are the critical values on the number line across the top. X minus 2 will equal 0 right at 2. It will be negative to the left and positive to the right. X minus 4 equals 0 right at 4. It will be negative to the left and positive to the right. In the first interval, the overall value of f of x will be positive because it is a negative times a negative. In the middle interval, f of x will be negative. Positive times a negative is a negative. And in the third interval, f of x will be positive. Because we want f of x to be less than or equal to 0, the solutions will be in the interval where f of x is negative. Because we want f of x to be less than or equal to 0, we will include these critical values 2 and 4 in the solutions by using brackets. So the solution is the closed interval from 2 to 4. This includes the endpoints 2 and 4. This next example is a little bit tricky because when we try to factor, we quickly realize that this is unfactorable. 8 can either factor as 2 times 4 or 8 times 1. Either way, there's no way that we can get a middle term of 5x out of this. So we need to use the quadratic formula to try to find the critical values. Here is the quadratic formula. For this problem, a is 1, b is 5, and c is 8. So we have x is equal to the opposite of b, so that'll be -5, plus or minus the square root of b squared, so 25 minus 4 times a, which is 1, so I won't really write it, times c, which is 8. All over 2a, well, 2 times 1 is just 2. But 4 times 8 is 32, so we have 25 minus 32, which is -7. You can't take the square root of a negative number, that's imaginary. That means there are no critical values. Even though there are no critical values, we can still make a sign chart. The lack of critical values means that f of x will not equal 0 anywhere. However, it will still be either negative or positive. It'll either be negative everywhere or positive everywhere. So let's just pick a value. 0 would be the easiest. Imagine that we put in 0 for all of the x's. So we put in 0 here and here. Then f of x would simply equal 8, which is a positive number. That means that f of x will be positive everywhere. We were looking for values of x that would cause f of x to be less than 0. Since f of x is always positive, this inequality has no solution. This next example is very similar to the last one. When we try to factor this trinomial, we quickly discover that there is no way to factor it. So let's use the quadratic formula again. X equals the opposite of b, so -2, plus or minus the square root of b squared, which is 4, minus 4 times a, which is 1, which I won't write, times c, all over 2a, so 2 times 1. But 4 minus 20 leaves a -16 under the radical. Again, you can't take the square root of a negative number. That's imaginary. That means that we have no critical numbers. The lack of critical values means that f of x does not equal 0 anywhere. It will either be negative everywhere or positive everywhere. So let's just plug in 0 and see what happens there. If we plug in 0 for these x's, these terms will be gone, leaving positive 5. That means f of x is positive everywhere. We were looking for values of x that would cause f of x to be greater than or equal to 0. Since f of x is positive everywhere, the solutions are from -infinity to positive infinity. Let's shift gears and talk about how to solve a rational inequality. The word rational just means that we have expressions that are in the form of fractions. The first step is to take these two separate fractions and combine them into one big old fraction. To do that, we need like denominators. So we notice that the denominator on the right has an x plus 1 in it. So we need to make sure that the denominator on the left also has an x plus 1. We can make that happen if we multiply by x plus 1 over x plus 1. We have to multiply by the same thing in the top and the bottom so that we are actually multiplying by 1, which does not change the value of the expression. The fraction on the left has x minus 6 in the denominator. So we need the denominator on the right to also have an x minus 6. We can again make that happen by multiplying by x minus 6 over x minus 6. So on the next step, we can combine everything into one big fraction, keeping the like denominator that we just formed. So we have a like denominator of x plus 1 times x minus 6. We will add together the numerators that we just made. Let's go ahead and distribute the 4 now. So that will give us 4x plus 4. And distributing this 2 gives us plus 2x minus 12. Let's combine like terms in the numerator. So we will have 6x minus 8 over x plus 1 times x minus 6. All of this is greater than 0. I am noticing that there is a common factor of 2 in the numerator. So I feel like factoring that out as well. So I'm going to take out this 2, and that will leave behind 3x minus 4 over x plus 1 times x minus 6 is greater than 0. Critical values are the values that cause f of x to either equal 0 or to be undefined. When you have a rational expression, you will often have some of each. A fraction will equal 0 only when the numerator is equal to 0. So setting 3x minus 4 equal to 0, we get x is equal to 4 over 3. 2 cannot equal 0, so you can just ignore that. A fraction will be undefined when the denominator is equal to 0. This will happen when x is equal to -1, if we set the first factor equal to 0, or when x is equal to +6. That's what we get when we set x minus 6 equal to 0. So we have 3 critical values. Let's make a sign chart. So here are the critical numbers across the top. We need to find out whether these factors are positive or negative in each interval. Let's start with 3x minus 4. This will equal 0 at 4 over 3. It will be negative to the left and positive to the right. X plus 1 equals 0 right at -1. It will be negative to the left and positive to the right. X minus 6 will equal 0 right at 6. It will be negative to the left and positive to the right. Now for the overall value of f of x in each interval. In the first interval, we have an odd number of negatives. That will give us an overall value of negative. In the middle interval, we have a negative times a negative. That's a positive. The single negative in the third interval makes the overall sign a negative. And of course, all the positives in the last interval make f of x positive. We are interested in the values of x that will cause the function to be greater than 0. That means the solutions will be in this interval and this interval. Before I write up the final answer, you might have noticed that I ignored the 2. You can ignore the 2 because it is a positive constant. If I wanted to, I could put it on the sign chart, but 2 is always positive, so I would simply go plus, 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 plus. Adding a row of positives does not change the overall sign of the function, so there was no need to even write it down. On the other hand, imagine that the 2 had been a -2. Then I would have to include it on my sign chart, because if I go back and add a row of negatives, that will make each of these values the opposite from what you see now. The positive intervals are from -1 to 4 over 3 and from +6 to infinity. Notice that we will always use parentheses at values of x that will cause f of x to be undefined. So even if this had been greater than or equal to, we would still use parentheses at -1 and 6 in our solution. But what about 4 over 3? 4 over 3 is the value of x that causes f of x to equal 0. We are leaving it not included on this problem because we want values of x that cause f of x to be greater than 0, not equal to 0. However, if this had been greater than or equal to 0, then we would have put a bracket on the 4 over 3. Again, the values that cause f of x to be undefined will always get parentheses, regardless of whether or not you have a little equal to sign with your greater than sign. Anyway, this is the final answer. Last one. This problem has one extra step to it. We need to get 0 on one side, so I am going to subtract this entire fraction from both sides of the inequality. In other words, I'm basically going to move this fraction over to the left and make it negative. So now we have this. We need to combine these two separate fractions into one big fraction. In order to do that, we need like denominators. The fraction on the right has an x plus 5 in the denominator. So we need an x plus 5 in the denominator on the left. We can accomplish this by multiplying by x plus 5 over x plus 5. The denominator on the left has this extra x. So we need the denominator on the right to also have an extra x. So we will multiply by x over x. Now we have like denominators, so we can combine these into one fraction. We keep the like denominator of x times x plus 5. Then in the numerator, we have x plus 5 minus x. And all of this is greater than 0. Simplifying, we notice that the x minus x cancels out. So now we have this. Also, I decided to change this to a greater than or equal to problem so I can show you when to use a bracket and when to use a parenthesis. Let's find the critical values. These are the values that will cause f of x to equal 0 or to be undefined. A fraction will equal 0 when the numerator is equal to 0, but 5 cannot equal 0, so there are no values that will cause f of x to equal 0. A fraction will be undefined when the denominator is equal to 0. This will happen when x is equal to 0 because of the first factor, or when x is equal to negative 5, which is what we get when we set x plus 5 equal to 0. Now we can make a sign chart, starting by putting our two critical numbers across the top on this number line. We need to decide whether these factors are positive or negative in each interval. Of course, x itself will be negative to the left of 0 and positive to the right of 0. X plus 5 is equal to 0 right at negative 5. It will be negative to the left and positive to the right. In the first interval, f of x will be positive because a negative times a negative is a positive. Similarly, a negative times a positive is a negative, and a positive times a positive is a positive. The solutions are the values that cause f of x to be greater than or equal to 0. So the solutions will be in the intervals where f of x will be positive. So the solution set goes from negative infinity to negative 5, union 0 to infinity. Notice that I used parentheses on the negative 5 and the 0, even though we have greater than or equal to 0. That's because f of x is undefined at 0 and negative 5. And undefined values cannot be included in the solution set.